Imagine having the power to grasp things that are out of reach, or having the strength to lift objects that would normally be too heavy. Does this sound like a superhero story? It's closer to reality than you might think. We're talking about the fascinating world of bionic hands. These are not just figments of science fiction, but real, tangible marvels of modern engineering. They have the potential to change lives, restore lost abilities, and even provide newfound capacities. Think about it. The ability to play a piano for those who never could, or the power to hold a loved one's hand again. Intriguing, isn't it? And we're just scratching the surface. In fact, we recently embarked on a project to build a bionic hand for a YouTuber, an endeavor that's as challenging as it is exciting. So, how does one build a bionic hand? Stay tuned to unravel the mystery. Building a bionic hand begins with a detailed blueprint, much like constructing a house. So, how exactly do we go about drafting this blueprint? Well, it's a process that requires careful consideration and planning. Much like any architect, we start by visualizing the final product. We imagine a hand fully functional and capable of performing a variety of tasks. But, unlike an architect, we're not working with bricks and mortar. We're dealing with sensors, motors, and artificial tendons. The first step in our blueprint is deciding on the individual components that will make up our bionic hand. We need to think about the types of motors we'll use to drive the movement of the fingers. We'll also need sensors to detect pressure and positioning. Then, there's the artificial tendons, which will mimic the function of human tendons, allowing the fingers to bend and flex. Once we've determined the necessary components, it's time to think about their placement. This is where our blueprint starts to take shape. We need to ensure that the motors are positioned in a way that will allow for smooth, natural movements. The sensors must be placed strategically to accurately detect pressure and positioning. And the artificial tendons. They need to be arranged in a way that mimics the human hand as closely as possible. Now, we have a collection of components and a plan for their placement. But how will they all work together? This is where the blueprint becomes more than just a sketch. We need to create a system of connections, a network of wires and circuits that will enable all of these components to communicate with each other. This network is like the nervous system of the bionic hand, transmitting signals from the sensors to the motors and allowing the hand to respond to external stimuli. This, in essence, is the blueprint of a bionic hand. It's a complex web of components, connections, and circuits, all working together to create a hand that can grip, touch, and feel. It's a testament to the incredible advancements in technology and a glimpse into the future of prosthetics. With a blueprint in hand, we're ready to bring our bionic hand to life. Now comes the exciting part, assembling the bionic hand. Our journey begins with the individual components, each crafted with precision and care. These aren't just pieces of metal and plastic. They're the building blocks of a revolution in human potential. First, we start with the palm. It's the base of the hand, a sturdy frame that will host all the other components. We attach the metacarpals, the bones that will form the structure of the fingers. The precision of these parts is crucial. A fraction of an inch off, and the whole hand could malfunction. Next, we move on to the fingers themselves. Each finger is assembled separately, piece by piece, joint by joint. We use a combination of miniature motors and cables designed to mimic the complex movements of a human hand. It's a meticulous process, requiring patience and a steady hand. Once the fingers are assembled, they're attached to the palm. This is where we start to see the bionic hand take shape. It's a breathtaking sight, watching this piece of technology come to life. But the assembly isn't over yet. The next step is to install the sensors. These tiny devices will detect the user's muscle movements, allowing them to control the hand as if it were their own. They're installed in strategic locations, designed to maximize responsiveness and control. Finally, we install the power source. This is what will bring our bionic hand to life. It's a small, rechargeable battery capable of powering the hand for up to 24 hours on a single charge. It's installed in the wrist, out of sight but never out of mind. Once all the components are in place, it's time for a test run. We flex the fingers, rotate the wrist, and test the sensors to ensure everything is working as it should. It's a moment of truth, a testament to the hours of work and dedication that went into its creation. As the pieces come together, a bionic hand begins to take form. This is more than just an assembly process. It's a journey into the future, a glimpse into a world where the impossible becomes possible. A bionic hand is more than a mechanical device. It's a piece of technology that needs programming. In the realm of bionics, programming is the invisible thread that binds together hardware and human intention. It's the magic that allows an array of sensors, motors, and mechanical fingers to transform into a responsive, intuitive, and lifelike hand. At the heart of our bionic hand lies the microcontroller, a compact yet powerful computer that interprets and executes our programmed instructions. This microcontroller receives input from sensors embedded in the hand and the wearer's residual limb. These sensors detect muscle movements, temperature, and even pressure, providing a rich tapestry of information for our programming to interpret. Our programming then translates these sensor inputs into specific actions. For example, a certain muscle flex might be programmed to trigger a finger curl, while a different movement may open the hand flat. It's this complex dance of input and output, guided by our programming, that allows the bionic hand to perform a wide range of tasks, from gripping a coffee cup to playing a piano. This programming process involves a lot of trial and error, tweaking and adjusting. We use a coding language that the microcontroller can understand, and we often have to iterate on our code, testing and refining it until we get the desired results. It's a painstaking process, but it's also incredibly rewarding. Every line of code brings us one step closer to a functional bionic hand that can truly enhance the wearer's life. And it's not just about functionality. Our programming also ensures that the bionic hand responds in a smooth and natural manner, mimicking the fluid movements of a biological hand as closely as possible. This is where artistry meets engineering, as we strive to create not just a tool, but an extension of the human body. With the programming complete, we have a functional bionic hand. Now, it's time to put this marvel of technology to the test. Will it meet our expectations? Will it truly extend the capabilities of the wearer? Or will it need further refinement? Stay tuned to find out. Creating a bionic hand isn't just about assembling and programming, it's also about testing and adjusting. This is the crucial stage where we ensure the bionic hand doesn't just look good, but also works well and accomplishes its purpose. After the assembly and programming stages, we've got a visually appealing bionic hand. But does it function as we want it to? That's what we're going to find out now. Testing a bionic hand involves a comprehensive series of checks. We start with the basics, checking the mechanical movements. Do the fingers flex and extend smoothly? Does the wrist rotate without any hitches? This is about ensuring the mechanical parts are working in harmony, providing the range of motion we want. Next, we move on to the more complex aspects. The sensors, the motors, the microcontroller, they all need to be in sync. If the sensors don't accurately detect the user's muscle movements, or if the microcontroller doesn't interpret these signals correctly, the bionic hand won't respond as desired. So, we test the hand's responsiveness to different user inputs, making sure it can perform a variety of tasks. And then comes the adjustments. Based on the results of our tests, we fine-tune the bionic hand. Is a finger moving too slowly? We can adjust the motor speed. Is the hand not grasping objects tightly enough? We can tweak the sensor sensitivity. These adjustments are about refining the bionic hand, making it not just functional, but also efficient and user-friendly. This process of testing and adjusting isn't a one-off thing. It's iterative. We test, we adjust, and then we test again, continuing this cycle until we're satisfied with the performance of the bionic hand. Every iteration brings us closer to perfection, to a bionic hand that can truly augment human capabilities. And so, after rigorous testing and adjustments, our bionic hand is ready. It's not just a piece of tech, it's a testament to human ingenuity, a tool that can change lives. And we've ensured it's the best it can be. Building a bionic hand is a remarkable feat, but its impact goes beyond the creation process. This innovative piece of technology, at the intersection of biology and mechanics, has the potential to revolutionize the quality of life for many individuals. Imagine, if you will, a world where loss of a limb doesn't mean loss of ability. Picture a musician, able to strum the guitar once more, or a chef, deftly slicing and dicing with precision. Bionic hands can make these scenarios a reality, opening up a realm of possibilities previously unthinkable. But it's not just about regaining lost skills. Bionic hands can also provide a sense of wholeness, of identity, restoring the confidence that may have been lost along with the limb. It's about empowerment, independence, and the ability to face life's challenges head-on. And there you have it.